Hey, thanks for all getting here. This session was not on the agenda, so hopefully you're all excited to learn more depth about these announcements. We were really thrilled to be able to talk about some of this work. I'm Britt Johnston. I'm the Director of Product Management for Redshift, and thrilled to be able to talk to you.
Hi, I'm Andy Caldwell. I'm a Senior Principal Engineer in Redshift and the Technical Lead for AQUA, and I'm super excited to talk to you about it today.
So we're going to, in our session today, we're going to go through, really unpack the announcements, the two major announcements that we've talked about in the major keynote yesterday. And so we'll do that. I'll kind of cover the front end of that on RA3, and then Andy will come up and drill into the details on AQUA. We really want in this session for you to get another level of detail on those announcements. We want to make sure you can understand how you can apply that to your particular needs or problem space. And then we want to give you kind of go-dos of things you can go take away from this and go do next in your own personal journey. Just show of hands, how many people out there right now are current Redshift customers? So a lot of that. That is wonderful. One of the great things about this event is getting to meet all you. So I really appreciate that. One of the things, not only are we announcing hardware acceleration at this event, just overall, Redshift is really accelerating. And I don't know if you've noticed, but the announcements just keep coming out. We're trying to make the system easier for you to use. And I want to drill into some of those details. We do appreciate that there's so much that's coming out. It can be a little overwhelming. I do want to tune you into the what's new announcements that we do. They're just a couple paragraphs of description, but they really are very clear descriptions of what is new. So I encourage you to really look at those when you're trying to keep up with what's changing. And virtually everything we do, we have a special what's new on there. And the team spends a lot of time to make sure that those are easy to understand. You're in great company. The Redshift is used by tens of thousands of customers, and we're really excited to be able to talk about that. As a collective, we process with Redshift exabytes of data every day. It's amazing how much information is flowing through these systems. And actually, the fact that we are all using these systems in a cloud is what makes some of the innovation possible that we're working on. A couple things I want to draw your attention to. One is that from a Redshift perspective, central to our strategy is supporting your needs to build a data lake. We believe there's so much information that you need to be able to keep track of, catalog, and refer to. Some of it is not the stuff that you need to run your everyday business. Some of the stuff is reference information that you may need in the future. And making sure we build a system that allows you to reach out and access that data, whether it's in the Redshift system itself, whether it's in S3 in your data lake, or whether it's even in other systems. That is fundamental. So that data lake support and integration with other AWS services is something you'll continue to see us improving. Performance is what our number one factor we want to make sure we deliver to you as a service beyond base security, building a secure platform. And we don't compromise in any way performance. So all the decisions we make are really around maximizing performance, and we won't implement something that doesn't improve the performance of the system. So there's a very high bar for new capabilities. At this point, and we've done measurements this week using all the code that's currently in production across all the cloud vendors, Redshift is 3x faster, at least 3x faster than all the other solutions that are out there. We're really proud of that. It's something we work really hard on. And that's something that we look at every day. We have a team that constantly monitors how that's doing. And in fact, it was kind of exciting. The minor changes that we made even in the last week actually sped things up even more. And so it's fun to be able to see that, and it's great to be able to share that. Making sure we deliver that performance at the absolute lowest cost is also important to us. We're constantly trying to push cost out of the system to make sure that you can do as much as you can with your analytics dollar. We want to make sure that the system is easy to use. You know, this is an interesting change that's evolved over time. When we first brought Redshift onto the scene, it was pretty understandable that you were going to have a fairly healthy administrative process for that. That's what we were all used to. But what time has really changed, and the expectations that all of you have, is that we make it even much easier to use, and we're constantly pushing on that. At this point, we've got advisors for almost all the tuning kind of parameters that you might have. So you can go in, and we've got expert systems that are monitoring those systems, machine learning models, and they'll tell you how to improve your system. And it's pretty straightforward to be able to take advantage of that. Making sure we scale is also important, and we'll touch a little bit more on that. But making sure you can have an elastic system that can scale both in terms of the amount of data that you need, but also in terms of the number of queries and the number of users is paramount. We need to be able to let you grow with your organization's need. The foundation that we build all this on is security, and making sure we provide integration with all of the AWS security features that are out there, making sure we're compliant with all the various regulatory certifications that you need to be able to put your data into Redshift is vital to us. So hopefully those summary gives you some context for that. I do want to pull out an aggregation of a lot of really cool things that we've done just in the last 6 months has led to 2.35 times speed up of Redshift. And this is create a cluster, load some data, and start asking queries. No tuning, no nothing. That kind of level of speed up. And a lot of that is because of the techniques that we're using. We're shifting the techniques from things that require tuning to things that don't. And those are exciting. A few of them here. We'll talk a little bit more about our encoding. That helps speed things up. Using interesting techniques around bloom filters and query techniques to make those fundamental query operations more efficient. Getting a more sophisticated planner. In fact, central to the announcements we did around Federated Query is the fact that the query planner is getting really smart. It knows how to take advantage of not only Redshift's internal capabilities, but also other engines' capabilities. We've evolved our statistics mechanisms to where rather than requiring a full scan of data, they can do subsets, basically statistically valid subset of data, and build statistics off that. So we're able to be more efficient in that processing. Anyway, I wanted to illustrate this so you just get an idea of some of the things that are built into the system. You don't really have to do anything to take advantage of this. This is just what you get out of the box. Now, if we take all those innovations you saw and we put them kind of on a timeline and sort them by different capabilities, we've been spending a lot of time on performance and scalability, ease of use, and our data lake integration. The two that we're going to focus on here today is the RA3 and AQUA. And so we want to drill into that in more detail. Before I do that, though, I want to talk about a few technologies that I think are central to what we've been doing. And the AQUA talk is going to build on top of these. So let's talk about these a little bit. The first one is encoding. You know, encoding data is not a very exciting topic, and it's actually surprising that we can innovate so much on this. This is essentially how we take a piece of data and turn it into bits that we put on a disk. Well, it turns out by looking at this problem again in the context of modern hardware, we've been able to build a better encoding model. And it's really significant. You can see here that over other techniques, significantly less storage is involved. So we're able to essentially compress out up to 70% of the data of already established techniques that are good. And that's pretty shocking. To be able to get 60 to 70% compression on top of what's there is really great. So that means that over time, storing data in Redshift, actually, it gets smaller and smaller as we get better at that. But it also, not only did we get more compression, but we actually sped up the system. And the way we did this is take advantage of effectively hardware acceleration, not with specialized silicon, but using what are called the SIMD instructions that are part of modern processors. The modern processors are adding these additional instructions that let us perform parallel operations on data. And taking advantage of those really specialized instructions lets us do that. So that thinking of looking at hardware, understanding how we can take advantage of it, is something that we've been looking at for a while, and it's what really led us to the evolution that brought us AQUA. So I wanted to give you that as a first point there. The next one is around federated query. And this is something that we announced here. Now, the particular instance that we're showing at the moment is around doing queries across not only your Redshift data, but also being able to reach out into RDS and Aurora PostgreSQL databases so that you can take operational data and mix that with your data in your warehouse and do that. In fact, a great demo that we have around this, if we had time today, I'd do it, is really having a single query that touches the latest up to the second data and some historical data that's very relevant to the business, but then some archive data that's really old. And being able to look across all of that with a single query, one stored in the case of the demo in RDS PostgreSQL, the middle is stored in Redshift, and the old data is stored in S3 in an open format. And so being able to cross the boundary is there. But having a query engine that can deal with that kind of complexity is fundamental to what we're doing. And leveraging that technology is something that's in what we're doing as well. Another important technology, and this is something we actually announced last week, but are really emphasizing here, is materialized views. I think this is really important and something that we're going to build on. Essentially what this does is let you define a view and then pre-compute the results of that and maintain that. What that means is a very complex query, we don't have to execute it every time and collect all the data and do all the processing. We can instead do that once and then reuse that over and over again. So materialized views and the rich implementation that we have, really richer than any other system, allows us to have very complex join processing in there, very complex filtering and aggregations, so that the complex query can have have really useful data set. It's interesting for all sorts of purposes there. It eases things like migration because you can capture very complex things and have those pre-computed so you can use them. Another technology I want to put a light on is machine learning. I'd mentioned that originally when we had brought Redshift to market, people expected that there would be some amount of administration work necessary. But that's increasingly no longer accepted. Well, how are we going to fix all those things? Well, the way we've done them in some cases is provide better algorithms that don't require anything. But in some cases, really what we need to do is provide expertise on how to choose what to select. And so we're creating machine learning models based on all the data that we can look at, all the queries. Essentially, we can understand, not at the detailed level, but at the abstract level, all the queries that are being running across all of the Redshift systems in the world, and take that learning and pick out the best ways to do things. We can do things like figure out small queries and how to optimize those better. We can do things like figure out what sort of distribution or sort keys need to be selected based on the underlying data. And taking what typically would involve a human administrator studying the data, we can replace that with automation. And so that ability to to leverage machine learning as part of the service is something that's going to make it easier and easier to operate over time. So those technologies, hardware acceleration, query optimization, materialized views, and machine learning are really fundamental to how we're pushing forward, and it'll be fun to show you the things that we're doing based on that. So let's dive into the first of those two technologies, RA3. It's the new third-generation instance type for Redshift. And you can take RA3 compute nodes and build them into a cluster. It has a couple of really important new capabilities. One is that we are moving to what we call managed storage, which is, so rather than having you limited to the storage that's local to the machine, we're actually expanding on that. But we're doing it in a pretty special way. You know, one of the things we want to avoid is introducing anything that's going to slow down the system. And so making sure that we're doing this in a way that is performant is fundamental to what's going on. You know, the reason we're able to get those performance results that I showed earlier is because of this approach. So a combination of a managed storage design, and we'll dive into that a little bit, taking advantage of high-speed caches, and some of that has to do with how fast flash storage is getting. We'll talk about that in some more detail later. And then the ability to leverage high bandwidth networking as part of that. So the approach that we're taking is to allow you with RA3 to essentially scale or size your warehouse based on what your compute needs are, and then only pay for how much data you need. And so it's a little bit different approach to solving that. But the managed storage underneath has a lot more complexity than you might think in terms of that. And we'll worry about that as a service. So you can pay separately for storage and compute on that. And you don't need to change anything about how you operate your current system. So if you have a current Redshift cluster, we'll go into some details about how you can do that. First, let's dive into a little bit on what RA3 is inside. If you were in Andy Jassy's keynote yesterday, you heard about Nitro system and how we're continuing to build on that. The RA3 uses the Nitro system, and so it's able to offload some of the processing that occurs and that normally would occur on a CPU into dedicated processors. And so that delivers more of the CPU for your workload, and that's really important. On top of that, we've built out the ability to scale these in a tremendous way. So our largest RA3 cluster, and you can go build one of these today if you want to, has 6,144 CPUs, or vCPUs, 48 terabytes of RAM, and can support 8 petabytes of storage. Anyone have a system in the audience that is not big enough for? Any takers? We have one. I want to talk to you about that because I can make this even bigger, but I got to have someone that needs it. So come talk to me about that. Seriously. And I'm excited to learn about that. We really think RA3 is going to provide you with unmatched performance at an unbeatable price. You know, you can scale your system with this in an incremental way, and the pricing is really aggressive that we chose for this. As a guideline, think about, for most of you are probably on DS2 clusters. As a guideline, think of RA3 as essentially twice the performance of your current system with 2 times the storage for the same price. So it is a really simple decision as to whether you want to move there. And as we said earlier, it really gives you 3 times the price performance of any other solution out there. So it's something we're very excited to be able to talk to you. We do have, and I'll get into some details about migration guidance, but what we've announced here today or yesterday is the RA3, what we call 16XL size. We are going to have an RA3 4XL size, sort of a mini version of it, and that will be available coming soon. We're not disclosing a date yet, but we're working hard to make sure that you have access to that as well. And that will just give you more options in terms of how you want to size things. So for migration guidance, I want to walk through a little bit of what that looks like, and I'll give you some examples too that are part of that. Most of those DS2 8XL clusters out there will get that 2x improvement if they migrate in a 2-to-1 ratio. So let's say, for example, today you had 8-node DS2 8XL cluster. You could move that to a 4-node RA3 cluster, and you'd get that benefit that's there. Now, you can migrate in other ratios. That's fine. Your particular, remember we talked about size of system based on your compute needs. Some people may have their existing cluster size based on storage capacity, and they're not as using the compute as heavily. So it may be that you can go with a different ratio, 3-to-1 or 4-to-1 in terms of that. So that would mean, let's say you had 8 nodes today, you could go down to 2 nodes if you were not using those CPUs much. So you can size that system based on what you think you need there in terms of a ratio. If you have a DS2 cluster that's really under 10 terabytes of data, we think you're probably better off waiting for the RA3 4XL. You don't have to, but that might be a better in terms of matching your current cost structure, something to think about. So we want to be upfront on that. The next one is for those of you that have DC2 clusters. If you've got larger DC2 clusters, and often those are pretty constrained in terms of their storage capacity. So if you have a larger DC2 cluster, you can potentially really benefit from that by expanding to RA3. Now, our general advice is doing that in a 3-to-1 ratio. So let's say you had 9 nodes today, you go to 3 nodes in your system as a ratio, and that will give you price equivalent system. Generally, the performance should be slightly better to similar in terms of overall, but you'll have 8x the storage capacity. So the limit that you're probably fighting today on DC2 is storage. That goes away. 8x is a pretty big improvement there. Now, the reason it's not as big of a difference performance-wise at this ratio is the DC2 is a pretty great processor. It's dense compute, right? So that compute ratio that's in there, the amount of compute per dollar, if you will, is pretty good. And so you're not going to see a huge performance improvement in terms of query performance. You will see massive improvement in your storage capacity. So that's something to keep in mind. Again, if you have a DC2 cluster with 5 to 10 terabytes of data, you might want to consider staying on DC2 for now, and we'll update you as we get more information on the RA3 4XL that we talked about relative to that. We're not ready to get into the advice on that. So you've gone through, you've made your decision that you want to migrate. I hope everybody here is thinking about that. And what does that mean? Well, it's actually really easy. Essentially, all of the formulas we talked about here, you don't need to worry about memorizing those. They're all built into the console. So you point the console at an existing system. It will recommend what you should migrate it to, and it will step you through that migration. And you can do it 2 major ways. So restoring from snapshots, the easiest and the fastest, and that will take the data as rapidly as possible and build a new cluster. That's the preferred way by many people. If you want to kind of start over from scratch and load the data directly and essentially relay it out on the system, you can use the classic resize approach, and that will give you that. That retains the full flexibility of elastic resize in the system. So there's something, if you're sizing your system a lot, or changing the sizing a lot, or adjusting the sizing a lot, then that's something to consider. But for most people, doing a restore from snapshot, that will get you up and running really quickly on that system. So that's the consideration on migration, some guidance there. And remember, the console has that all built in. So you don't need to take notes, or you just fire up the console and look at that. So for real world experience, I want to give you some examples. And these are real customers, and they took their systems, went through the process of migrating, and ran their workloads and did some comparative performance analysis on that. So moving from DS2, maintaining the same cost, but getting much better performance, which was our sort of fundamental goal there. We had a customer move from 14 nodes of their DS2 system to 7 nodes of RA3. And their experience was 2.1% X faster performance on that. Pretty happy with that change, because there was no price cost, right? They just got double the performance at the same price, which was exciting. Different customer moving from DS2, they had a really ETL-intense workload. And one of the benefits of RA3 is because of that high bandwidth networking capability through that system, and the ability to offload processing in moving network traffic in the system. The net of that is they got a great increase in their ETL load times. And so for them, they went from 16 nodes to 8 nodes, but their ETL was 1.3 times faster. So they were really happy to see an improvement in their ETL load times for them. And for them, it was on the edge of what was acceptable, and it brought them into a really comfortable place. And so they weren't putting as much stress on the system from an overall CPU perspective. They did see much better performance as well as part of that. So the last example here is moving from DC2. And in this case, we had a customer that moved from 15 nodes of DC2 to 5 nodes of RA3. And for them, queries are about 1.25 times faster. So significant performance increase for them. They saw a benefit. Remember, now they have 8 times the storage capacity. So really unlocked the ability to get at that capability. So a couple quotes here from different customers in terms of their own experiences. I'll let you read theirs, but I won't go through there. But you can see 2 times performance, 1.9x times the performance. So these are real-world examples from great customers of ours that we work closely with. Fayez, Jonathan, and Stephen were our great partners that we work closely with. I want to share, I talked earlier about RA3 brings managed storage to the table. And I want to share a little bit of our vision about this. Don't think of this as a roadmap so much as our intent, where we're going with this. We think based on hardware acceleration, we can build managed storage so it can scan data faster than a CPU can. So that fundamentally unlocks some new capability. So we're trying to take advantage of that. We think we can get to a point where turning on a new system, pausing and resuming systems can be completely instant. And so we're excited to work on that. We want to build a system that's auto-tiered, so the temperature of the data as it moves, it moves between the systems. And what that really does is let you optimize your cost. Right? If we can minimize the amount of really expensive componentry in the system, we can keep the price of the system low. And so we want to be able to take advantage of that and optimize it, as I talked about, for networking and flash. So hopefully that gives you a little deeper dive into what RA3 is about. Hopefully you have some confidence to go and look at the console and look at migrating your system as part of that. But next what we want to do is have Andy come back up on stage here and drill into AQUA and tell you about that. So I'll turn it over to him.
Thanks, Britt. Hi, I'm really excited to be here and tell you a bit more about AQUA. So the RA3 that Britt just talked about, we think this is a really substantial step forward for Redshift. It expands the performance envelope of what's possible with a cloud-based data warehouse, and it introduces a new degree of flexibility to be able to trade off rapidly and dynamically between the amount of compute and the amount of storage. this is pretty excellent evolution, but it's really the start of Redshift's evolution and not the end. So I wanted to take the rest of the time today and talk to you about what's our next step there and where are we headed. So as we started thinking a little bit more about data warehouses and data lakes and how to combine them, a lake house, if you will, we sort of looked at the architectures of traditional data warehousing and thinking about what's really there, what are the trade-offs this presents, and what can we do? And traditionally, there's basically two ways of building a large-scale data warehousing product. You have the one approach, sometimes called shared nothing, where you attach fast local drives into each of the compute nodes of the cluster, you hydrate the data there, and you execute off that. And this allows you to get really as much of the performance of that fast local storage as you possibly can. So it's great for speed, but potentially at the expense of scalability, and particularly dynamic scalability. And the other approach is to take your storage and put it in a large, possibly multi-tenant, network-attached storage system, and then run off of that. And this gets you a lot of flexibility, right? I can very easily independently scale my compute and my storage, and that's awesome. But now I'm moving all my data over the network. And so this presents a potential networking bottleneck. And so as we were looking at these, we were wondering, what can I do? How can I get the best of both of those worlds? Is there a way to do something better? And in designing something better, we had a couple of key design requirements that we felt like we really must adhere to. And the first was performance. We hear a lot from customers that they really value Redshift's industry-leading performance. And so any solution we would present would have to preserve that or double down on it. And the second is scalability. Everybody's got rapidly growing data volumes. Andy talked about in his keynote yesterday the new scale of data. And so we felt like we needed a solution that will support both of those. And I think we've come up with one and maybe done even a little bit better than that. So I'm really excited to talk to you today about AQUA. AQUA is the Advanced Query Accelerator for Amazon Redshift. AQUA is a new distributed, hardware-accelerated caching execution layer for Amazon Redshift. AQUA enables Redshift to run up to 10x faster than any other cloud-based data warehouse. It is 100% compatible with Redshift as it exists today, because those are Redshift clusters sitting at the top of that diagram. Onboarding to AQUA is trivial. If you have a Redshift RA3 cluster, you're using your Redshift cluster, you've loaded your data in it, you're sending your queries there, you do exactly the same thing with AQUA. It's completely managed by Redshift and by AQUA. So there's no change at all in workload, there's no change in schema, you don't have to change your queries, you don't have to do anything but turn it on. And with that, you get unparalleled performance with your Redshift RA3 cluster. So the RA3s are available today. As Britt said, you can launch the ginormous 128-node RA3 cluster now if you'd like to. You can sign up for a preview of AQUA for your RA3 cluster, and we'll go GA with that mid-next year. So I want to take the rest of our time and sort of dig in a little bit, peel back the covers a bit and talk to you about what AQUA is, how it works, what runs in there, and see if we can get a little more understanding of what our roadmap for this kind of disaggregated compute and the roadmap for data warehousing at Redshift. So I mentioned before that we've got these sort of two approaches, the sort of local disk and the network-attached shared disk, and there's a speed and performance trade-off in there. And hybrids are definitely possible, right? The RA3 is a hybrid, and it provides pretty great speed and pretty good flexibility. But AQUA is sort of a next step in that direction in really taking the managed storage that comes with the RA3 and kicking it up a notch. AQUA is a push-down, hardware-accelerated caching layer. It stores your data in fast SSDs that are locally inside each node in the AQUA layer. But it's not really a caching layer, and it's not really a storage layer, because that's not how it's used. So in the traditional sort of network-attached storage model of data warehousing, your data sits in the big warehouse, and every time you need to process data, the cluster says to the storage, please give me table A, or please give me this block from some column of table A that needs to be processed. And that data goes from the network-attached storage over the network into your compute cluster where you process it. And that's the inefficient part. That's the middle part where you're sending all the data from where it's stored to where it's computed. And that's the potential bottleneck. Even with the super fast enhanced networking that AWS has announced, that's not nearly as fast as the drives can produce data or the CPU can consume data. So we needed a solution to that. And that's really the key differentiator between AQUA and any of the architectures, the macro architectures for analytic warehouses. We're not pulling the data over, we're sending the computation to the data. So AQUA isn't really a caching layer, even though it caches data, because it's not used like a caching layer. It doesn't have a storage-like interface. It has a functional interface. It has a computation interface. So if you think about what your analytics systems are doing, analytics platforms are needle and haystack finders. They are summary and grouping generators. They take enormous amounts of data, and they find the bits you care about right now, or they compress and aggregate those bits into something smaller. And finding needles in haystacks and generating summaries, these are compressee operators. These are data filter operators. The data that goes into that part of your query is much, much bigger than the data that goes out. And the part of query execution that we're talking about here is the scan and the aggregate. And if I look across Redshift and do some sort of fleet-wide analysis, what we see is that there's a 10-to-1, sometimes as much as a 20 or 30-to-1 ratio of the data that's going into those filters and compressors, the scan and aggregation operators, versus what's coming out. And that's our opportunity to do something better and build a disaggregated computing structure. So when you send a query to Redshift, Redshift automatically determines what's the scan and ag part, what's the data reduction operator, and it sends that as a subquery over to AQUA. And that's the interface that's different from it being a storage layer. It's that sending of a subquery to our hardware-accelerated caching layer. So the subquery comes over, and AQUA can then execute that subquery against fast local SSDs. So we get the speed of the local disk execution for the part of the query that really benefits from it, the part that's processing the largest portion of data, the scan and the ag at the bottom of the query execution tree. And so we pull that off the SSD, we execute it, and we send only the results back over the network. And since the results are at a 10-to-1 or greater in ratio, we're filtering out so much data in that scans and ags, and that's how we avoid having the network be a bottleneck. So with that, you get exactly the same kind of query execution from your Redshift cluster on exactly the same data with exactly the same schema, but we're pushing the data reduction operators to a remote store. And this gives us the sort of best of both worlds, the ability to have the speed of doing the high bandwidth, the high data operations against local store in the AQUA nodes, and the flexibility of having this shared multi-tenant network-attached storage layer. And that's where we're headed. So as we started thinking about AQUA, and how we could really build the best possible system, it was clear that this needed to really sing in terms of its ability to scan data and do scans and aggregations. And since we're building a system exactly for that, we wanted to really go all the way. And so we started by looking at the hardware. And we came up with something that I think is kind of interesting and actually really important, not just for AQUA, but for the way computing is structured and done in general. So we looked at the trends in bandwidth, in throughput, in hardware components over the last, let's say, 7 years. And bandwidth is really what matters here. This is a bandwidth-intensive part of query execution. It's the scans and the ags. You're streaming columnar data through that filter or that aggregation operator just as fast as you possibly can. And that's the key component for performance here is bandwidth. And when I look at the performance and the bandwidth and its change over time of hardware components, we see something interesting. The SSDs have gotten 12x faster over the past 7 years. 12 is an awful lot. This is a combination of improved flash technology, better controllers, NVMe interfaces, 12x over the last 7 years. By comparison, if I look at the bandwidth of a CPU socket, and here for bandwidth, I'm using total aggregate DRAM bandwidth I can send into that CPU. The bandwidth of the CPU is only up 2x over that same 7-year fan. So we have a factor of 6 in terms of the growth rate of throughput of these components. Essentially, SSDs are getting faster, much, much faster than CPUs are getting faster. And for a variety of business and technology macro trend reasons, that's not going to change. This gulf is going to widen. We are not the first or the only company to have observed this. But I think in some ways, we're uniquely positioned to be able to take advantage of this. This observation that drives are getting faster, much faster than CPUs are getting faster, is the thing that's motivating computational storage, which is an industry buzzword. It's being used a lot by various venture capitals and component groups. But it's not really had a huge impact on what end users are doing today. And so when we're looking at this, we felt like this was our opportunity to take this observation and turn it into something that we could deliver to customers and really affect what people do with their data. And the reason I think we're uniquely positioned to be able to do that is that when you move computation, and that's really what computational storage is about. It's about fixing this gulf by taking the computation from the CPU and shoving it as far down inside and close to that storage as you can possibly get. When you do that, you change the interface. This no longer just looks to the rest of the system like a storage device. I put my data here, I get my data back. It now looks like a computation interface. And when you do that, I haven't just changed this component. I have to change its device drivers. I have to change the way it's mapped in the operating system. I have to change the application that's running on top of it. And so doing this effectively and really getting the benefit of those super fast SSDs requires engineering all the way across the stack. And so that's what we did with AQUA, actually. We built a completely custom node, ground up. We're leveraging the AWS Nitro chips to do hardware-accelerated compression and encryption, decompression and decryption. We've built a bespoke instance that has a unique architecture that connects those drives and those hardware-accelerated components. We designed and implemented a streaming, multi-core, hardware-accelerated processor specifically for analytics, and we put that in an FPGA, and we connected it directly to the high-speed storage devices that are there. And so we built ground up, starting from AWS custom chips all the way through the hardware and the physical interface of the box and the device drivers that run on there and the operating system and the application and the execution layer, all the way up into how this connects to your Redshift cluster. And by engineering across all of these layers, we're able to take advantage of that divergence in speed and really build the fastest scanning and agging thing we can possibly build. And then we leverage that by putting logic in the Redshift cluster that will take, when you access a table, and I've cached your hot data in AQUA, Redshift carves out all of the scanning and agging operations that are going on the table, and it pushes them down. And then we run them in this scale-out, distributed, hardware-accelerated layer where we've hot cached your data and send the results back up. And so the combination there is what gets us this 10x faster than any other cloud-based data warehouse. So we think this is pretty exciting. I'm actually super excited to talk to you guys about it. And we think it will transform really the way that you process the very large and growing amounts of data that we all have. So one more thing. Britt talked a little earlier in the hour about materialized views as a new feature that's available for Redshift. And I wanted to kind of tie that into what we're doing with AQUA, because these fit together really well as part of a seamless whole of what we're building. If you think about what a materialized view is, Redshift's materialized views can handle joins across multiple tables and aggregations and things like that. And you're taking a complex query that runs big joins or whatever you're doing, and you're incrementally updating and producing a table. And then when you execute on that table, what are you doing? You're doing a scan and an ag. Well, AQUA is really, really great at scans and ags. So these two work together really seamlessly. We can incrementally do your complicated joins and then hardware accelerate the scans and the aggregations that happen on the resulting data. So I think this is actually a really exciting combination. And it's a sort of glimpse into our vision for the future and how we take AQUA and what it's really great at and then tie it into the rest of the Redshift system. So I would encourage you to sign up for the preview of AQUA on your Redshift RA3 cluster. All right, so just summary, a little bit about what we've covered. So hopefully you've heard and understood some details about the new Redshift features, about the RA3, and about the AQUA system that we've just announced this week. I hope this helps you understand what our technology vision is for where Redshift is today and where Redshift is going, and how that can tie into your plans for data warehousing and data lakes. So thank you very much.